All right, welcome everyone to the ATN seminar. Today, our speaker is Robyn Brooks, who will be telling us about computing the matching distance of bi-persistence modules. So, floor is yours. Thank you so much.
Great. Thank you so much for organizers for letting me come talk, and also for running all the cool seminars and conferences that they run. You can tell I'm a little sick, so hopefully you guys will be able to understand me through your talk. But yeah, so today I'm going to be talking about computing the matching distance for bi-persistence modules. So this is joint work with a group of awesome mathematicians that I met at a Women in Computational Topology workshop in Australia. Asilata Bapat, Celia Hacker, Claudia Landi, Barbara Mahler, and Elizabeth Stephenson. So today in this talk, I'm going to talk about work from two different papers that we've been working on together. So one of these papers works out the theory of computing the matching distance, and then we had to write an additional paper on the implementation of this computation. So in the talk today, I'll start by introducing bi-persistence and the matching distance with an example. Next, I'll introduce a framework in which we try to find candidate lines in parameter space on which to compute the matching distance. Our original framework didn't work exactly the way we thought, so we had to refine it using something we call switch points. So I'll introduce those. And then at the end, I'll tell you kind of how we, our long journey of implementation and how that led to a second paper. So let's get started. We're all familiar with this single parameter persistent homology pipeline. We start with data and a relevant parameter. We use this to build a simplicial filtration and subsequently a 1D persistence module. And then we obtain relevant summaries / invariants. So we know and love this pipeline. We have complete invariance of the persistence module, like the barcode, and we have stability with respect to the bottleneck distance. But because we're mathematicians, and even sometimes because it is useful to allow our data to vary across multiple parameters, we want a similar pipeline for more than one parameter. So the things I'm going to show you for the multi-parameter persistent homology pipeline, I'm going to show you in 2 dimensions, but they can be for n parameters. So going from data to filtration, that kind of first step, there's a lot of ways to do that. Let's assume we've already done that step. And here we have a filtration indexed over R2. So in this example, our simplices are added at integer coordinates. And we can visualize the filtration by showing the simplicial complexes at those coordinates like you see here. So we notice we have inclusions between any pair of points in R2, which are comparable in the product order. So next, we apply homology and we get a multi-parameter persistence module, right? Our inclusions in the filtration become morphisms between homology groups at comparable parameter values. And then finally, we look at kind of the last step of that pipeline. And this is the first place where the pipeline kind of changes from the 1D case for the following reason. Well, it's true that we can, any persistence module that's defined over a poset can be written as a direct sum of indecomposables. 1D persistence modules are pretty nice in that those indecomposables are intervals, so they're nice little regions in the parameter space. This doesn't end up being true for n greater than 1. The space of indecomposables is really complex, and therefore the space of multi-parameter persistence modules is really complex. So in particular, it's not possible to guarantee that the indecomposables of your module are going to be parameterized by nice regions in parameter space. So in multi-parameter persistence, we rely on partial, not incomplete invariance for now. So one such partial invariant is something called the rank invariant. This is a function that is defined for comparable pairs UV in the parameter space. And the value of the rank invariant for UV is going to be the number of linearly independent homology classes which persist from U to V. So this is not unique. It's possible for 2 persistence modules to have the same rank invariant but not be isomorphic. But at the very least, you know, if you have 2 different rank invariants, then you're going to have 2 non-isomorphic modules. To compute the rank invariant, we can use a fibration of parameter space. So we notice that each line with positive slope in parameter space gives you a one parameter filtration, and that induces a 1D persistence module. So we have these kind of modules restricted along lines in parameter space. And in one dimension, rank invariant information can be obtained from the barcode / like persistence diagram or vice versa. Moreover, if you want to compute the rank between U and V kind of in your, say, bi module, you can compute this as the rank between U and V on the restricted line between U and V. So you can obtain rank info from the bi module for a line, and again, vice versa. And this idea of fibration of parameter space with lines can also be used to kind of extend the bottleneck distance for 1D persistence modules to the matching distance. So let me tell you about kind of our main character here today. The matching distance for two modules Mn is defined as a supremum over lines with positive slope of the weighted bottleneck distance. So what we do is we take our two modules, we slice them with the same line, we compute the bottleneck distance along that line, and then we weight that bottleneck distance to kind of normalize across lines and ensure stability. So this is our matching distance. Let's look at an example. Okay, so here I have two really nice kind of simple bi-persistence modules. They're both rectangle modules. Each of these colored blocks indicates an interval module defined over that region, and then M and N are kind of the direct sum of those two modules. So over here I have a blue block and a red block, and I can see they overlap here. And I have a big blue block, and it's kind of covering that red block, so that becomes purple. So if I want to compute the matching distance between these two modules, I need to compute the weighted bottleneck distance on all possible lines. So we'll start easy, and we'll look at lines with slope 1, so diagonal lines. If I want to compute the weighted bottleneck distance for lines with slope 1, the weighting factor ends up being 1, so I'm just computing the bottleneck distance. And I take, some random line with slope 1, maybe y equals x plus 6, and I look at the restricted module along those lines. I can see my intervals then kind of represented along this line with the red and the blue intervals there. And what I see is that when I restrict this line, the modules M and N are actually the same. So they have a bottleneck distance of 0. This is not the only diagonal line, nor line in general where this is true, but specifically for diagonal lines, I can see all the diagonal lines kind of outside of this region in the middle. I'm going to get the same module when I restrict to that line for M and N. So they all will have bottleneck distance 0. Okay. So if we want a diagonal line that where the modules aren't identical, I can look at this line here, y equals x plus 2. And I see I don't actually have identical modules, so I can compute the weighted bottleneck distance for this line. So for purposes of computing the cost of matching these intervals to compute the bottleneck distance, I've written kind of the lengths of these intervals. And here, the length is going to be the maximum difference between either the x values or the y values of the endpoints of the interval. So for this red interval in module M, right, I have endpoints 6, 8, 0, 2. I take the difference, 6 minus 0 or 8 minus 2. It's going to be the same because this line is diagonal, and I get a value of 6. And I'll erase that so you can actually see what the value is. Okay. So to compute the matching distance, right, I need to look over all possible matchings where I either match one interval from N with one interval from N, or I match one interval from M to the diagonal, right? And the cost of matching two of these intervals is going to be the difference of the lengths. So if I wanted to match, 5 with 7, the cost of that matching would be 2. Or the cost of matching those two bars, right? And if I wanted to maybe map the interval 4 to the diagonal, I would compute the cost of that as 4 over 2, so just 2. Okay, so the bottleneck distance is the infimum over all possible matchings. We can just kind of go through these because there's not a lot of possible matchings. And I see that there's a minimum cost matching, which actually sends blue for M to red for N, and vice versa, red for M to blue for N. And so I get a bottleneck distance of 1. My weighting factor, since it's diagonal, is 1, so I get a lower bound for the matching distance, which is 1. Okay. And again, kind of direct computation, a little bit of clever stuff shows you that this is going to be the diagonal line, which has kind of the maximum weighted bottleneck distance. So let's look at kind of one more line. Let's look at something that is not diagonal. So in this case, the weighted bottleneck distance is going to be weighted by 1 over the slope of the line. So since my line has slope 11 over 7, the weighting factor is going to be 7 over 11. And again, I've written kind of the lengths of these intervals, and I can compute a minimum cost matching between these restricted persistence modules. And matching blue with red with blue is going to give me a bottleneck distance of 3. Okay, so I again obtain another lower bound for the matching distance. Now it's 21 over 11. So if you want to compute the matching distance, you can kind of keep doing this process, maybe find some cute relationships between lines, and eventually try to find a supremum, some line that has the highest weighted bottleneck distance. Or you can try to be a little clever about it, and we can notice that there are some sets of lines that have the same bottleneck distance. So for example, right, I have this line here, right? If I were to take this line, I'm gonna, oh, can you guys see that purple? Maybe not. I'll write in a really bright color. Okay. So I'm gonna kind of fix that point at the point 711, and I'm gonna rotate counterclockwise, right? And I get a new line. If I don't rotate too much, I still have the same bottleneck distance along this line here of 3, but I'm getting something with a flatter slope, which gives me a larger weight. So I get a larger weighted bottleneck distance and a larger lower bound to the matching distance, right? And it turns out that this is generally true. We are able to identify subsets of lines for which it's possible to determine the largest weighted bottleneck distance in that set. So if we want to compute the matching distance, our goal then becomes trying to partition lines with positive slope into these sets where we can determine one line which has the maximum weighted bottleneck distance on that set. And if we find finitely many sets, right, we can obtain a finite set of candidate lines from which to compute the matching distance. And that makes this, you know, supremum calculation a maximum calculation. Okay, I'm going to drink a little water and you guys tell me if you have questions. No, everybody loves it. Great. Okay, cool. So before I tell you how we do this partitioning, I want to mention some related works. And these are, you know, definitely not all possible interesting related works. But first, I just want to like bring up exact versus approximate computation. There are some pretty great algorithms which compute an approximate matching distance, which is going to be a lower bound. And this is really, really useful because as it turns out, computing the exact matching distance is kind of hard and pretty expensive. And then there are kind of 2 other groups that I want to point out that have devised methods for computing the exact matching distance. So this first group that I call the extended Pareto grid group, they compute the matching distance for bipersistence modules that are obtained as homology of sublevel set filtrations. And the way that they do this computation is using something called the extended Pareto grid. This is a collection of curves and lines to find the sublevel sets. It's pretty cool. And then there's another group, maybe I'll call this the dual group, that uses point line duality to identify this set of candidate lines with maximum weighted bottleneck distance by representing these lines with positive slope as points in the dual plane. And then they kind of subdivide that dual plane into regions with an identifiable maximum. Okay, so our approach, it works directly on lines in parameter space, and it kind of has two steps that I'm going to talk about. So first, for a given module M, we can identify sets of lines where lines in the same set have a bijection between the restricted persistence diagrams. Okay, once you kind of have that, then for a pair of modules M and N, we refine these equivalence classes to sets of lines that have the same, that share a same optimal matching with respect to the bottleneck distance. So what I mean by that is when you're computing the bottleneck distance, there's going to be at least one matching of persistence diagrams which has cost equal to the bottleneck distance. And so we'll say that like such a matching which attains the actual cost of the bottleneck distance is optimal with respect to the bottleneck distance. Okay, cool. So in order to generate these sets of lines, or I might slip up and call them equivalence classes, actually I definitely will do that. So sets or equivalence classes of lines, we restrict ourselves to a subset of modules, which are nice in the following way. So these modules have the property where there is a finite set of critical parameter values. So for a module M, we have a set CM, from which we can compute the rank invariant. Okay, that's just kind of what this all says. So we restrict to these types of modules because they allow us to easily determine rank invariant information and therefore persistence diagrams along lines. And they also, like these kinds of modules, we can also easily obtain these equivalence classes of lines which have persistence diagrams, which are in bijection. So I want to show you very briefly kind of like how this is done, generating these equivalence classes that have persistence diagrams, which are in bijection. So the next couple of slides, they actually come from a past AATRN talk that I gave in 2020 on computing the rank invariant from critical parameter values. So if this is interesting to you, like you can go look it up. Man, 2020, long time ago. So here you can see the bifiltration I showed you earlier. This bifiltration now has a bunch of notation on it. That's a compatible discrete gradient vector field because in our paper we were finding critical values using discrete Morse theory. So don't worry about that. I've highlighted in yellow the places in the filtration that are associated to critical parameter values. And in this case, it's indicating like the entrance of a critical simplex entering the filtration. But just generally, like if you're not finding your critical values using discrete Morse theory, these critical values, these critical parameter values are kind of indicating a place in your bifiltration where you observe a change in homology. I think on the last slide I said that like if you have a finitely presented module, then you could also obtain your critical values as like the set of grades of generators and relators. So, you know, you could do that as well. So we view these critical parameter values in parameter space. It's just like a collection of points. And how these points are distributed and how lines with positive slope separate these in the plane determine how the restricted persistence diagrams along lines look. So to kind of see this, we want to observe that for like these multi-parameter persistence modules obtained from these, or like the nice class of multi-parameter persistence modules I've told you about, where the homology is kind of determined by a finite set of critical values, the changes in homology along a line are going to happen exactly at the places where that line intersects the positive cone of a critical value, right? So like, for example, C1, maybe like a critical simplex is entering the filtration here. Then if I want to know where it enters this line L, I look exactly at the place where that line intersects the positive cone for that critical value. So these intersection places with respect to these critical values and also how they are partitioned, right? So C3 is, you know, on the left of this line and these four are on the right. That's going to completely determine like when I can have changes in homology along my line. And so it's kind of determining the persistence diagram. This also means that when two lines separate the critical values in the same way, kind of like on left and right, the persistence diagrams along those lines are in some sense equivalent because, you know, the critical values are kind of pushing in the same way. So birth-death activity is happening in like the same combinatorial order. So what we get from this is an equivalence relation on lines. We call it tilde C. C is our set of critical values. The overline just means we actually have to close this set of critical values under least upper bound to really identify all the places where kind of the homology might change. But if I have two lines that are equivalent with respect to this equivalence relation, it just means that they separate, they like partition the critical values in the plane in the same way. Okay, so if I have equivalence between lines with respect to this equivalence relation, I'm actually able to define a bijection gamma between the persistence diagrams along those lines. So cool, why am I telling you all of this? Well, so if we go back to the matching distance, right, this is the supremum over the weighted bottleneck distance. Bottleneck distance is an infimum over cost of matchings between persistence diagrams. Well, it turns out that we can actually extend this bijection gamma between persistence diagrams to one between matchings of persistence diagrams, right? So if I have two equivalent lines, L and L prime, and then I have a matching between the persistence diagrams of ML and NL, I can use the bijections between the diagrams with respect to M and with respect to N to obtain now a matching between the restricted diagrams along L for M and N. Okay, so I can get this matching, and kind of even nicer, this bijection between matchings also allows me to compute the cost of that new matching from the original and from information about L and L prime. Okay. And maybe even nicer, if I fix a matching between two restricted lines, two diagrams restricted on a line, then there is both a direction of translation or and a point and a direction of rotation that will not decrease the cost of that matching. So I'm going to kind of show you guys this in a second. But what that means is that we can translate or rotate a line within an equivalence class until that line hits a critical value without decreasing the cost of that fixed matching, right? So that kind of indicates that lines through critical values are local maxima with respect to the cost of a fixed matching. Okay, so again, I'm bringing up this example. In this example, the critical values are just going to be corners of the rectangle. And that actually means that this line that I've shown you here is in its own equivalence class. But if I want to look at a different equivalence class, like I was showing you earlier, I can take lines that are fixed at this point, but kind of rotate, and any line that I can rotate between 0, 0 and 4, 0 is going to be in the same equivalence class with respect to critical values. It separates them in the same way. And we saw that we could rotate this line here and get an increase in the weighted bottleneck distance, right? So we're kind of like, we have this fixed matching, we rotate, that's going to increase the weighted bottleneck distance. And this is kind of where the framework breaks down a little bit, because you can observe, you're like, okay, cool, Robyn, let's like rotate, keep rotating in that direction. Let's keep increasing the weighted bottleneck distance. And if we rotate it all the way until we hit a critical value, we get this line here through 0, 4 and 7, 11, right? And well, I see that the modules are identical on that, so they have a weighted bottleneck distance of 0. So somehow I started off with, you know, some weighted non-zero weighted bottleneck distance. I rotated, that was increasing it, but then at some point, the weighted bottleneck distance started decreasing and it went all the way to 0, right? And the reason that this happens is because not all lines in this equivalence class have the same optimal matching for the weighted bottleneck distance, right? So the original one was matching blue to red, red to blue, right? But as I rotate this here, eventually there's going to be a point where the optimal matching switches to red and blue to blue, right? So this is kind of the issue with our framework in generating equivalence classes using just critical parameter values, right? We can make sure to only like to not decrease the cost of a fixed matching, but the weighted bottleneck distance is an infimum over all matchings, right? So even if we know the optimal matching, right, we might rotate or translate to a place where that matching is no longer optimal, and then you kind of don't know which way to translate or rotate. It's a big issue. Okay. So to fix this issue, what we need to do is to refine our equivalence classes so that there is at least one matching which is optimal with respect to bottleneck distance on all lines in the equivalence class, right? If we do that, then we can in fact choose a direction of translation or rotation, which doesn't decrease the cost of that matching. And then the local max with respect to bottleneck distance is going to be through points which determine these like new refined equivalence classes. Okay. So I'm going to tell you how we're going to refine the equivalence classes, but first I want to address one little issue, which like maybe people thought about, or maybe I'm talking so fast that you didn't even have time to think about it. That's okay. So we're kind of moving through like lines by translation and rotation. If I translate a line with positive slope, still going to have positive slope. But if I rotate a line with positive slope, it is possible for me to eventually get to a line that does not have positive slope, right? And if I do so, I'm going to have to either get to a vertical or a horizontal line. And the issue here is that the weighted bottleneck distance is not defined for these. So if I truly want to kind of follow this pattern of translation and rotation, I can't get to a place that's bad, right, where I'm undefined. So we need to do a slight adjustment here. What ends up happening is we see that we can avoid rotating to vertical or horizontal if I can always rotate towards the diagonal. Okay, so what we end up doing is adding in a point at infinity in the parameter space. So we view parameter space as a subspace of projective space. We add in the point at infinity 0, 1, 1, representing diagonal slope. And what that does is it breaks our equivalence classes now into two pieces, right? So I'm, have an equivalence class that partitions the critical values in some way, but then I can break that into two for lines that do it with slope greater than 1 and slope less than 1. So without getting kind of too much into this, this ensures that we can always find a line that isn't vertical or horizontal on which the matching distance is obtained. We can ensure that we can always rotate towards the diagonal. We never have to rotate too far away. And this also allows us to define the weighted bottleneck distance for vertical and horizontal lines as a limit. So it's not clear that we always have to include the diagonal. There are definitely like toy examples and edge cases where like the matching distance truly is only obtained on a diagonal line, and you do kind of have to add that in. But we're going to see actually that like this partitioning of equivalence classes via slope that actually kind of makes some sense with the framework that I'm going to tell you about in a second. Okay. So going back to this idea of identifying equivalence classes that have an optimal matching that works for all lines in that equivalence class. In order to do this, we have to determine where these optimal matchings might switch, right? So optimal matchings might switch if there is a line where the two matchings have the same cost along that line, right? So again, kind of looking back at that example, I had the, red-blue matching was optimal, and then I was rotating, and at some point, right, I passed kind of through this place where the red-blue matching and the red-red, blue-blue matching were the same, and then the red-red matching became optimal, and the red-blue was no longer optimal. So in order for, the optimal matching to switch, there has to be a line where they are the same, okay? And we're able to determine lines where this happens, where two matchings have the same cost, because all such lines always pass through a specific point. And we call that point a switch point, right? It's not just one point, there are many of these. These switch points are generated by looking at quadruples of critical values, because for our modules, the cost of a matching is realized as the difference between the pushes of critical values on a line. So switch points are generated by triples or quadruples of critical values whose like pushes on the line, when appropriately separated and paired, generate the same cost. So that was really a mouthful, and also I don't know this is something that's like much better seen in a picture. So let me kind of try to justify this for you. So in this example, I have four critical values, U, V, U, W, X. Okay. So I choose to kind of pair these, like my pairs are going to be U is paired with V, W is paired with X, and I have to choose a specific like push configuration, which is I want U and W on the left of the line and V and X on the right. Okay. So this choice of pairing and the push configuration gives me a formula for this point omega, right? I compute M2 and then I compute M1 and then I can compute omega, right? And this omega has the property where any line through this point, the distance between the push of V and the push of U, so this distance here, and the distance between the push of W and the push of X is the same. Okay, so that'll be true on any line through omega, right? And what does this mean? Well, it means if there's a matching whose cost is realized by the push of U and V, and then another matching which is realized by the push of W and X, then the cost of those matchings are the same on this line L, right? And then moreover, right, if either of those matchings was optimal, then this L might be a place where that optimal matching changes, right? So again, I'm going to kind of like draw this. I didn't factor drawing into my time, so maybe this will make me go over, but that's okay. I like drawing anyways. So I have this line L prime, and then I'll draw another line L double prime. Oh, maybe I don't want that one. I think I want this. Right? So if I look at the push of V on this blue line and the push of U, this is kind of my new like distance. And I can see that the push of the cost of kind of matching U and V is no longer equal to the cost of matching W and X. This is a lot bigger, right? Those things are no longer equal. So, this is going to be kind of not an optimal matching on L prime. And if I look on this other line, I look at, again, kind of this is now the cost of matching U and V, and well, actually W and X push to the same points, the cost of matching them is 0. So now this is, matching U and V is no longer the optimal thing to do kind of on this line. Or maybe better said, the matching which matches U and V does not have minimum cost, okay? So this is kind of what's happening. If we rotate down through here, we go L prime, L, these matchings kind of have the same cost, and then I go to a place where now the cost of matching UV is more than W and X. Okay, cool. So we obtain this omega point here from a quadruple, U, V, W, and X. It's possible to also obtain omega points or switch points from triples. So this is a triple kind of in the same push configuration that generates a switch point. There are other push configurations which generate switch points. Here I have my pairs are kind of split by the line. You can also have one pair on one side, one pair on the other. You can also have 3 points on one side, 1 point on the other. Okay, but the whole point is that creating these equivalence classes using both critical values and switch points to partition them guarantees that no possible matchings have equal cost. So in each equivalence class, there is at least one optimal matching, which remains optimal for all lines in the given class, right? And then what I can do is I can find the weighted maximum bottleneck distance through rotation and translation. Okay, so that's kind of like a part, this is, the first kind of theory paper that we wrote. Good news, switch points are computable. And when we do, in fact, refine our equivalence classes by adding these in, we can identify a finite set of lines from which to compute the matching distance. I'd say moreover, like thinking back to those related papers, the other groups that compute the exact matching distance, they also have some form of like switch point in their framework where they're finding these places where optimal matchings with respect to the bottleneck distance might change. Okay. And though we kind of have a different, different formulas because we have different notation, like a lot of these switch points are the same. Okay. The bad news is that it turns out there are a lot of switch points. Our only input is the critical values themselves, not information about how these points relate and generate points in the persistence diagrams along lines. So we can't really rule out any quadruples or triples with that like module specific information, right? Like, and similarly, like we can't know if a particular quadruple is going to generate an optimal matching. We just know that it, matching them would be some cost, and maybe that cost is equal to another cost. So we conclude our first paper with the following algorithm. In the dual space paper, the algorithm for the matching distance is basically the same. So in the primal plane, it looks like this. We have our modules M and N. Okay. We determine some set of critical values. We close that under least upper bound. And then we determine the set of switch points from the set of critical values. And so this is kind of like our second paper. And I'm going to talk really quickly about that in a second. But once we have this set of switch points, right, we determine our finite set of lines by generating lines that pass through two distinct points. So the first is like passing through a critical value or a proper omega point, so a point in the plane. And then the other can also pass through like a critical value, a proper omega point, or it can pass through one of those omega slopes. So you need to check kind of like all lines through critical values with a specific slope. Okay, so once we have a line, we compute the diagrams, right? Then we compute the weighted bottleneck distance, and since we have a finite set of lines, we get, just output the maximum. Great, cool. So back to kind of this step 3. So once we, wrote this paper, we were interested in kind of implementing it, and so the first thing we started doing was trying to generate these, the set of switch points. And we started very brute force, just generating switch points for all quadruples and all triples of critical values. And that was a kind of stupid idea. It wasn't stupid. It was a good place to start. But it generated a lot of switch points that were really, really crazy and that we could kind of easily determine weren't relevant in the computation of the matching distance, right? So these were points where like I knew that a line through this point was never going to achieve the matching distance. And it was just like, why is this point here? So we decided we wanted to prune out sets of points that we know cannot be useful, right? And so there may be more sets of these points, but we identified 3 issues that would kind of render a candidate switch point from a quadruple to be invalid or bad. So the first issue is we don't want to generate a switch point for a quadruple where it's not even possible to separate those points with a line with positive slope anyways, right? If I can't actually get a line, I don't really have, I don't have a line with positive slope that separates these ways, or these points in that way. So I don't want to generate a switch point for that configuration. The second issue is kind of related, but a little more subtle. So issue 2 is when you do in fact have lines with positive slope that separate your quadruple in the way you want, but none of those lines pass through omega, meaning none of those lines actually have the property that the cost of the matching that generated these points is equal. Okay. And then issue 3 is kind of the easiest one. Sometimes when you make a switch point, it gives you a critical point or a switch point you already had. So you got to throw that out, obviously. Okay. So this is kind of the content of our implementation paper. We have several different like push configurations, and then we have these 3 issues, and we're addressing and kind of implementing in our algorithm ways to prune points that have these issues. So I kind of want to end with just showing you guys one of these possible cases. So this is the 3x1 case. So I have U, V, W, and X, or sorry, U, V, W on the left and X on the right. And so we wanted to identify such configurations and such quadruples where there would be no line with positive slope that separates the points in this way. X on the right, U, V, W on the left. And the way to determine this is by looking at the convex hull of U, V, and W. Okay, so we generate this convex hull, and then we use it to partition parameter space into quadrants, right? So the quadrants are such that like the convex hull of U, V, and W just lives in this like upper L. Okay, and in this case, there are two cases. The origin of these quadrants, this A bar, is either in the convex hull or it's not. If it is in the convex hull, like here on the left, then there is no way for any point in the entire upper left quadrant Q to be separated from U, V, and W um, by a line with positive slope. Okay, you can put your X up here, but this is not the correct configuration because I want X on the left and UVW on the right. So we can kind of look at the convex hull of this triple of points and we can determine if our point X is in this upper quadrant. And if it is, then it's going to be a switch point we don't want and we throw it out, right? If the origin is not in the convex hull, then I actually do have this little yellow region where, hey, I could put my X there and I can separate things with a line with positive slope. But anything in the convex hull or in this white part U, again, is not going to be able to be separated from UVW on the left with a line with positive slope. Cool. So we are done kind of implementing these pruning things. And right now we're finishing up this second paper by running experiments. And there are some takeaways here. The takeaway is maybe exact computation is really pretty expensive, even with the pruning, which actually does help quite a bit from like the brute case force. Like it's pretty time expensive and we're not using really fancy modules, so it doesn't seem like this is like a super practical computation, but it still is pretty interesting. And we do obtain, like even for very simple examples, cases where like our approximation, which is not the approximation that I mentioned earlier, but just like our approximation of like taking some uniformly distributed set of lines with positive slope and approximating the matching distance on that, there are cases where you do actually need to use these switch points to determine the exact matching distance, and the approximation can be kind of shitty. So once we finish experiments, we're going to let you guys know the details. And if you're interested in either of these papers that I've been talking about, this one is, the matching distance paper. This is like the theory paper I'm talking about. And then this is the implementation paper. Okay, thank you.
Thank you very much. Let's all unmute and clap briefly for Robyn. Hopefully Zoom will record it.
Ooh, okay, the image really helps.
The image helps indeed, right? Unfortunately, it doesn't seem to work for me, but maybe I can send you one as well. Yes, it works.
Yeah, thanks everybody. Oh, that one was pretty.
So do we have any questions from the audience at this point? While we're waiting for people to collect their thoughts, I'm maybe going to start with a with a bad one, but this is for bi-persistence modules, right? So do you think it's possible to at least like inspire some new approaches for a higher order modules as well, or is this not going anywhere? Is this not feasible?
I mean, that is a really lovely question. I agree with you. I think about that a lot. So maybe what I'll say is like the first step that we have, right, where we take this module and we make this bijection between persistence diagrams, that works for any dimension, right? You can do that. And when you're thinking about like lines are equivalent if they partition the lines in the same way, what that really means is like, in 3 dimensions or 4 dimensions, the positive cone of a critical value is going to be higher dimensional, right? And you can kind of break it up into pieces. And so you get equivalences based on like which face of the positive cone the lines intersect for each critical value. So there is an analog there. The generating the switch points is like very highly determined by these push configurations, right? So there's the push configuration of like 3 points on the left, 1 point on the right. We have this where like there are 2 pairs that are split by the line. We also have this configuration where like I have 1 pair on one side and 1 pair on the other. That is really dependent on being in the plane, right?
Yeah.
So and this is already like quite you need a lot. We like if you look at our papers, like there are cases aplenty.
Mhm.
So I don't know. I mean, I would like I think it's a really interesting question, and I bet there is something kind of like this going on, but it's just identifying like these lines in parameter space if in 3 dimensions where the bottleneck distance changes, right? Like now you have a bunch of directions you could translate or rotate, and it just becomes really complicated. So in order to kind of like understand that framework, I think there needs to be a little bit more thought on kind of like the mathematical tools you use to record this information of like what the
Mhm.
equivalence classes are, and then also how these lines are separating things. Yeah.
Yeah, gotcha. Okay. No, it's really cool because I keep thinking like for me, multi-parameter persistence is like this really complicated thing, but at least in the biparameter case, I always see some light at the end of the tunnel that is not an actual train, you know? So
Uh,
it's so I have that feeling that that something
yeah.
can be done there.
Yeah. Maybe the other thing I will say is like, um, even like finding so like even generating these equivalence classes, you can do it. Like even finding a representative line is kind of hard.
Mhm.
Like going from like the theory to like the actual computation is something kind of different.
Mhm.
Yeah, but that's something I do like to think about. So thank you for the question.
Oh, very happy. Thank you. Thank you for the great answer.
I have a
Any?
question. So,
Yeah, go for it.
have you guys tried to implement this at all?
Yeah, we definitely have. That's what the experiments are, right? So in the algorithm, right? Where is it? We use, we can use stuff from other people, right? Where it's kind of like we're inputting these for our experiments and then determining this. This is
All
kind of
right.
the implementation. And then this part is actually like, everybody kind of knows how to do that, like computing persistence diagrams along those things. Um,
And what language did you use?
So we are using a Python, if that's what you mean. I'm not an implementer. I'm a friend of implementers, a
Uh-huh.
colleague of implementers. But yeah, what we're kind of doing now is we're looking at experiments, compute like trying to compute the matching distance between just rectangle modules like I showed you before with like different numbers of rectangles. Um, and it's weird. We get really, really weird switch points that are like super far away from like the support of the critical values. Like you can have, like 4 critical values here, and you get switch points that are like just like straight lines that go up and out from the critical values, which is like very strange.
Hmm,
Um, yeah,
cool. Thanks.
yeah.
I have a loaded question too. The good. Um, so it's you don't need to motivate to me. I mean, it sounds super cool, but do you have any application in mind? Because it's always hard, right? We want to have everything at the same time. We cannot really think of application until we have tool. We cannot really think tool without application. So that's why I say it is loaded.
Yeah.
But have you played around with something?
Like an actual application, like a scenario where you get 2 modules. Those 2 modules have literal meaning, and the distance between
Mhm.
them has meaning.
Sort of, or anything. Let's say I let you interpret the application question as open
As
as you
I see
wish.
fit.
Yeah.
So short answer, no.
Mhm.
I'm not that type of I'm the type of mathematician that does it even if you don't need an application.
Oh yeah. That's why I say you don't need to
Um,
motivate it to me.
yeah, which you get. I will maybe reference, and this might not actually be a great answer to your question, but I know that, like, for example, climate scientists have like data that varies on a lot of parameters. And they've recently been trying to use bi-persistence as a way
Hmm.
to um identify topological features in a filtration that relate to these things called weather regimes.
Mm-hmm. Mm-hmm.
And so like I know this because like some climate scientists told me this and they were like, hey, can you help us? I was like, I don't know. But there's like a large, there was this MRC a couple summers ago, and there's a bunch of people that are trying to kind of use by persistence, essentially because like they do in fact kind of observe that one parameter isn't enough to capture
Yeah.
these weather regime topological features. So
Mm-hmm.
it's one application, which
Yeah,
doesn't
that's cool.
tell you what the matching distance would be in that case, but the distance between two like weather regime, I don't know.
Yeah, no, it's I do a lot of work that does technically application, but I have absolutely no idea what they are, right? So
Yeah, you're like, there's an application, I bet.
there is, I think it exists, the possibility of an application, and that's enough for me. So yeah. But thank you for the talk. It was super cool.
We have some other questions from the audience. Maybe I'm going to continue with a more like a sidetrack question. I hope it's not too much of a sidetrack, Robyn, but what did you observe like different types of filtration functions for biparameter modules that kind of make more sense in many cases? So what would you be typically using, or is this something where you say no, I'm just interested in the very abstract case and I don't really care about the specific use of filter functions, which would also be perfectly fine, right? I'm just asking with an applied hat on now.
Yeah. I'm gonna answer that in maybe not a way that's actually gonna answer your question. But right, so like kind of at the beginning of the talk, I was talking about like these nice filtrations, right, where you can compute or nice modules, right, where you can compute the value of the rank invariant from this finite set of critical parameter values. I would say like more generally, like I understand and do work with more like tame modules. And for a biparameter persistence module or an n parameter persistence module to be tame and obtained from filtration, that kind of that will put restrictions on kind of like what your filtration can look like. Right. So I don't know if that's exactly what you were talking about, but like in the context of like understanding generating the things you need to like do these computations in the way that we have done it, you need some sort of kind of reasonable behavior of entrance values of simplices and some discrete nature of that as well. And then kind of more abstractly and maybe a little more vaguely, some sort of, yeah, I guess maybe I'll just say like tame behavior of these entrance values of these like critical values that are changing homology, which then allow you to kind of determine how the behavior of the multi-parameter persistence module is throughout the whole thing. Yeah.
I think that's very helpful. I was more thinking in terms of like concrete implementations, like you have one distance filtration where I think this should hold, right? These are typically like tame, and then maybe like one based on local curvature or stuff like this. But no,
Yeah, okay.
actually
Yeah,
sounds like
and
a way
maybe to
better
answer,
question.
yeah, in that sense, like I know the climate scientists care about like density. Like they do the density RIPS filtrations a lot. Because they have like kind of I think that's something that people who want to like observe topological features of like dynamical systems, which like climate data is like data associated to a dynamical system. I think that can be kind of helpful, the density RIPS ones. Yeah.
Very nice, very nice. All right. Do we have any other questions? We're nearing the hour mark. not, I would suggest we thank Robyn again, and then we move to the offline session for questions. So thank you once again for being with us today, Robyn. A pleasure. Okay.